Hey guys, welcome to episode 23 of Short Bits by Shorty, the Enteral Nutrition one, aka probably my last Short Bits by Shorty ever. Get excited, I am. Stay tuned at the end of this video for a short message by me since it's the last video. It's my farewell message. Other than that, yep, stay tuned and let's get started. Okay, so we're gonna calculate the resting energy expenditure for a 30-year-old female, weight 65 kilograms, height 160 centimeters, admitted for pneumonia secondary to influenza using, number 1, the Harris-Benedict equation, number 2, the Mifflin-St. Jeor equation. So, using the Harris-Benedict equation, number 1, according to the Harris-Benedict equation, the resting energy expenditure for a woman is 655 plus 9.6 times the weight in kilograms, plus 1.8 times the height in centimeters, minus 4.7 times the age in years. So this girl is 655 plus 9.6 times 65 kilograms, plus 1.8, she's 160 centimeters, minus 4.7, she's 30 years. That should give you 1426. So resting energy expenditure using the Harris-Benedict equation is 1426. Using the Mifflin-St. Jeor equation, that's negative 161 plus 10 times the weight in kilograms, plus 6.25 times the height in centimeters, minus 5 times the age in years. Again, she is 161 plus 65 kilograms, 6.25. She's 160 centimeters. 160, that's right, 6.25. And she's 30 years old. That should give you 1339. Correct? Correct. Okay. So using the Harris-Benedict equation, you get 1426. Using the Mifflin-St. Jeor equation, you get 1339. Next example. Patient continues to decline clinically and required endotracheal intubation. Her Tmax for the past 24 hours is 39.5 degrees Celsius. She's breathing 18 times per minute, taking tidal volumes of 300 milliliters. We're going to calculate her resting energy expenditure using Penn State equation and the SCCM Aspen recommendation. So, number 1, using the Penn State equation, her resting energy expenditure is 0.85 times the Harris-Benedict equation using her actual body weight plus 175 times her Tmax the last 24 hours plus 33 times the minute volume from the ventilator in liters per minute. So it's going to be liters per minute. So, as we said earlier, her Harris-Benedict resting energy expenditure is 1426. So 8.85 times 1426 plus 175. Her Tmax is 39.5. Remember, that's in Celsius. 26. So how are we going to get the tidal volume in liters per minute? Well, I'll show you on this side. Okay. So she is breathing 300 milliliters. So you want the units in liters per minute. So you're gonna have the volume on top and the amount of times per minute on the bottom. So we're gonna do 300 milliliters over, we'll get to that later. So 300 milliliters is equal to 0.3 liters over, now how do you get the minutes? Well, she's breathing 18 times per minute, so it's 18 times per minute. So you know that multiplying 0.3 0.3 liters times your 18 times per minute would give you the units of liters per minute. So to get your tidal volume, you're going to multiply, in summary, multiply your volume times the number of times per minute. In short, if you don't want to logically go through the units and just memorize it, here is a way to memorize it. So your volume times your number of times breathing per minute. Logically, it makes sense because, unit-wise, it makes sense because 0.3 liters times 18 per minute gives you the units of liters per minute. So this would give you, but if you don't want to memorize, if you don't want to go through that, here's the formula for you. So your volume times the times per minute gives you 0.3 liters times 18 times per minute, which is 3.4 liters per minute. Or 5.4, sorry, I said that wrong. 5.4. 5.4, that's right, okay. So, let's see, 33 times 5.4. So 0.85 times 1426 plus 175, 39.5 plus 30. Oh, forgot to subtract 6,433. So at the end, subtract 6,433. 6,433. So 25, and that gives you 433. 1870. Now, using the SCCM Aspen recommendation equation, you get, let's see. So first we need to calculate her BMI. So first is her BMI. You know the units of BMI are in kilograms per meter squared. So she is 65 kilograms divided by, let's convert, so she's 100, she's 160 centimeters. Right, yep. So that is 1.6 meters. So 1.6 meters squared. Then that should give you, see, her BMI is 25.4. Kilograms per meter squared. So, according to SCCM Aspen recommendations, since her BMI is, let's see, she is non-obese, so, yeah, she's not obese because her BMI is less than 30. Non-obese. So that means her resting energy expenditure is 25 to 30 kcal per kilogram per day based on actual body weight, using the actual body weight. I'm on slide 12, by the way, if you want to see where I'm getting this. Slide 12. So 25 to 30. Okay, let's break this down. So let's start from the lower end. You can also go to the higher end. So kcals, 25 kcals per kilogram per day. She's 65 kilograms, right? 65. So the units cancel, kilograms cancel, leaving you with the units of kcal per day. So 25 times 65 would give you 1625. Now the higher end, which is 30 kcals per kilogram per day, times 65, weight in kilograms, actual body weight. Units cancel out. Always try to cancel units. Logically go through your units. Cancel with kilograms. That gives you units of kcal per day. That gives you 1950. That should give, yep, cool, that answers the question. So she needs between 1625 kcals per day and 1950 kcals per day. Let's see. Next question. Using the resting energy potential from the Penn State equation, calculate a goal enteral nutrition rate for a patient if the team wishes to give a promote ring continuously over 24 hours. Okay, so let's see. We know that promote, oh, here it is. Okay. Promote gives you 1 kcal per milliliter. kcal per milliliter. And you know your rate is always volume over time. Your rate's always going to be volume over time. You're trying to solve for a rate. So that can be either milliliters per minute, for example, milliliters per hour. Here, we want the units to be rate over 24 hours. So, let's see. So we know from the Mifflin-St. Jeor equation, the Penn State equation, she needs 1870 kcals. So we know from the Penn State equation, she needs 1870 kcals. We know the units here for promote are 1 kcal per milliliter. So to cancel out the kcal, you're going to divide by 1 kcal per milliliter. And when you switch the units, or divide, you switch the units, so 1870 kcal. 1 kcal per 1 milliliter. So the units for kcal cancel out. That gives you 1870 milliliters. You want it over 24 hours. As our question asked, you want this over 24 hours. So, remember, rate's always volume over time. So, over 24 hours. And you get 1870 over 24, 78 mils per hour. Right, so, key concepts of the question. You know your rate's always volume per time, so your final units have to be volume per time. You know, Penn State equation gave you 1870 kcals. Dividing that by the promote caloric density of 1 kcal per milliliter gives you the volume. Divide that by 24 hours gives you the mils per hour, which is your rate. So always check your units, make sure your units match. I like math because it's just playing around. It's like a puzzle. It's playing around with the units. I love puzzles. I love games. Puzzles are games. I love games. Video games. See me at video games. Okay. Next. The patient develops acute renal failure. That's awkward. Her potassium and phosphorus are both extremely high. What enteral nutrition product might be a better option? This one's not a math question. The answer is just Nepro. Because it has a lower density of potassium and phosphorus compared to the other products. What rate would provide her resting energy expenditure? Okay, remember your rate is always in milliliter or volume over time. So you know your units have to be volume over time for this answer. Caloric density of Nepro is vanilla. 1.8 kcals per milliliters. 1.8 kcal per mil. Let's see. Oh yeah. Okay, so using the same Penn State equation, you know her resting energy expenditure was 1870 kcals. So y'all know what you gotta do. 1870 kcals. Cancel out units. Divided by 1.8 kcal per mil. That means when you divide, you switch units around. Times 1.8 kcal per mil. Cancel out the kcals. Gives you 1870 mils. Divided by 24 hours gives you 43 mils per hour. Cool. Okay, I'm almost done. Oh, man. Okay, her goal protein of a patient's goal, not her. A patient's goal protein intake is 80 grams per day. He is currently, he is currently on Nepro, running continuously at 35 mils per hour, which is his goal and from nutrition rate. Do you need to recommend supplemental protein? If so, how many packets of ProSource would you recommend giving per day? Okay, so he's on Nepro. You know the caloric density of Nepro is 1.8 kcals per mil. 1.8 kcal per mil. Let's see. So total. So you know that every day, running continuous at 35 mils per hour, you know that every day he gets 1.8 kcals. How many per mil? How many calories does he get from Nepro per day? So he's on 35 mils per hour. So 1.8 kcal per mil times 35 mil per hour times 24 hours. Why did I do that? Because I wanted it per day. So one day has 24 hours. To cancel out the units, mils cancel out with mils, hours cancels out with hours. So this is the caloric density per day. That would give you 18 times 1.8 times 35 times 24, 1512 kcals per day. Stu, if he gets 4 grams of protein per 1,000 kcals. So hold on, let's go back. So Nepro. So you're trying to figure out how much protein is provided by Nepro. So here's your protein. It provides 45 grams per 1,000 kcals. So if Nepro provides 45 grams per 1,000 kcal, and you knew that he's on a 1512 kcal per day, so make sure units match up. 1512 kcal. Solve for x. That gives you how many grams of protein? He's on 68 grams of protein. So, if his goal is 80 grams, he is being underfed his protein, right? Because 68 grams is less than 80 grams. And you know that one packet gives you 15 grams of protein. So 68 plus 15, 83 grams of protein. So you need 1 packet of protein to get you from the 68 grams he's currently being fed to the 80 grams of his goal. Okay, last question. Yeah. Okay, and then my little tidbit, as I promised. Okay. So, a patient has basal energy expenditure of 1750 kcal per day. The team wishes to start a bolus tube feeding regimen with Jevity 1.2 kcal per mil. How many cans of Jevity should the patient receive per day? Each can is 240 milliliters. Okay. Let's see. So we know that he's receiving, or he has a basal energy expenditure of 17 kcal per day. So you want your final units to be in cans. So let's figure out how to get this in cans. So let's see, 1750 kcals per day. Divided by 1.2 kcals per milliliter. I'm getting that from here. 1.2 kcals per milliliter. Doing that so the units can cancel out. Kcals cancel out. And now you know that 1 can is 240 milliliters. So 240 milliliters, 1 can. I'm doing that because the milliliters cancel out, and now your units are can divided by day. So units are can per day, which is the units I'm looking for. Ta-da, it matches. So if you do 1750 divided by 1.2 divided by 240, you get 6.1 cans per day, which is equivalent to 6 cans per day. So a lot of it's just canceling out units and using formulas. Cancel out units to get your final answer. You pretty much know what to do. Also practice. Yeah, practice these. Talk them through with me. Walk them through with me. Watch these videos as many times as you want. Walk through these problems as many times as you want. Hopefully the unit cancellations make sense. If not, let me know. I can explain it a different way. Okay. Time for my little message. So, I hope you enjoyed all these videos. My favorite parts from you guys watching these videos and actually understanding medchem. I love when you all would ask questions during the medchem lectures and answer the questions that the professors posed to us. It made me proud because it made me see, oh, wow, you guys actually understand medchem. It's a teacher's favorite moment when the kids actually understand what they're teaching. Hopefully you guys learned why, or maybe gleaned, why medchem is important. It helps us understand why we do things. For example, from this enteral nutrition lecture, medchem is the basis for why you separate calcium carbonate and levofloxacin, or back in the past, why diazepam has a longer half-life than lorazepam, or why methamphetamine is much more potent as a stimulant than amphetamine. It's all about the chemistry, and if you understand the chemistry, you understand the science of pharmacy, which is why I love medchem. Once you understand medchem, you understand pharmacy. Hopefully, maybe. Anyways, I hope you enjoyed these videos. I enjoyed making them sometimes. I hope you enjoyed watching them, my little tidbits, shout-outs here and there. As always, feel free to subscribe, even though you don't have to anymore. And if you have any feedback, always feel free to leave it at pollev.com/CHRISTIAN RUI629. Hope you appreciated chemistry as much as I still appreciate chemistry. And I'm glad you guys actually understood chemistry from watching these videos. Thank you, and see you at graduation.